every covalent bond in your body came from sunlight. Basically, you're walking around a stored system of solar energy. You don't think about it that way, but that's really in reality what it is. So if you think about this now, we have this planet on which I'm just going to make a brief comment because I've been thinking about this for several years, and it's actually a really, really, really hard problem. We now have identified roughly 3,800 extrasolar planets. Most of these are around what's called M stars. These are young stars. They have a lot of energy. And according to Vicki Meadows and Jim Caston, if there's water on the planet, they can create oxygen without biology. Now, I have a hard time with that. And it means that the #1 biosignature gas that we subscribe to is really not truly necessarily a biosignature gas. So I'm not sure exactly now, and I'm sitting on this team of really smart people with Roger Summons, Vicki Meadows, Jerry Joyce, and so on, and asking the question, how would you know if there's life on an extrasolar planet for which you have no hope, ever, in your lifetime, in your children's 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 lifetime, of ever sending something to that planet physically to probe. So I'm going to leave you with that thought for a bit, and then I'm going to come back to that at the very end. So I spent a lot of time after I got to Rutgers, and I was thrown into, or I came to be part of this department. And I'm going to give you a secret, which I told Ken Miller when he tried to recruit me. I took one course in geology at City College as an undergraduate. One. And I liked it, but I mostly majored in chemistry and biology, so I double majored in this. The only course in chemistry that I didn't take was inorganic chemistry, which I took much later in my career. But, so I was thrown into this department and asked, what do you want to do? And I created a course, right, which is the history of the Earth system. And I had to learn not just geology from a book. I had to learn some geology in the field. So I've been to the field a few times, but I went a few years ago, actually now it's 15 years ago almost, with Munich Rossing, and then later on again to Greenland. And here I'm standing in front of the rocks, the top of Ishua. So these are 3.8 billion year old rocks. And you can see immediately that there's iron in those rocks. And you can also see immediately that these rocks are from some sort of sedimentary formation. So you know there's an ocean. What would become clear is that if you start to explore these, that there was an ocean. And the ocean had a rich amount of iron in it, which somehow precipitated at 3.8 billion. Now, if you start cutting into these rocks, you realize this is not truly banded iron formations, obviously, but if you start cutting into them, you realize that like the true banded iron formations, of which the archetypes are in the Pilbara or the Winnewar formations of Australia, what you see is oxidized iron. So there are several ways that you can oxidize iron in an anaerobic ocean. One is biological oxidation. So you can use the electrons on iron 2 photosynthetically, biologically, to fix carbon dioxide without oxygen. That's one hypothesis. Another hypothesis, which has been popularized by Emoto at Penn State and which has very, very little credibility today, I think, was that there actually was oxygen. We already had oxygen at 3.8 billion. Well, that falls flat when you start to look at the Farquhar paper in Science years ago of the mass-independent isotopic fractionation of sulfur, which would tell you, presumably, the interpretation of Mark Demons and Jim Farquhar, was that we developed an ozone layer at approximately 2.35 billion years ago. So then we went from a mass-independent to a mass-dependent isotopic fractionation of sulfur. If that interpretation is correct, then the oxygen concentration of the early Earth was very, very, very low, in spite of the fact that there was liquid water on the surface of the planet. Now, there's a third possibility, which becomes a very interesting one because we ignore it almost always in geology. And that is, can you populate an anti-bonding orbital of iron to generate and pop off an electron to make ferrous iron to become ferric iron? Can light do it? And the answer turns out to be yes. So you need UV light. So if you don't have an ozone layer, you can get that light to the surface of the planet, and you can generate oxidized iron, absent biology, absent oxygen. And that's the light to life. Now, when you do that, here's the gimmick. It's a sacrificial reaction. You oxidize the iron just becomes oxidized, it can sediment, it doesn't come back, it doesn't do anything. But if I look in you and your bodies, you have iron in your bodies. You use it in proteins, which I'll explain in a few minutes, but it's catalytic. It's not sacrificial. So it's moving energy or bond energies around, rearranging bonds in a way that is repetitive again and again. That's the catalysis part. So here's the question that I'm really, really, really focused on. Is I know that we can generate non-catalytic sacrificial reactions of transition metals, in this case, for example, iron. But how do we get to the catalytic reactions of life? How do we get to something that is so far away from thermodynamic equilibrium it's in a new steady state? That's a really, really, really hard question. So that's what I'm trying to answer before I die. And I'm always looking at this very famous, obviously, the number one thing that you learn in introductory geochemistry, the Victor Goldschmidt plot. So the Victor Goldschmidt plot, you have two elements here, hydrogen and helium, which are the primordial elements of the Big Bang. And by the way, the astronomers call everything beyond that a metal. Okay, so I was at a metals in biology meeting at a Gordon conference a few weeks ago, and that, you know, obviously they're focusing on transition metals, and I told them, you know, for astronomy, all of these are metals. That was kind of amusing. So we have two ends of the spectrum here. We have the hydrogen-helium pair, and uranium, thorium, potassium 40. So these forces here, the energy that can be generated here by fission, creates a heat engine for this planet. And the energy that's by fusion is generated by our star. And Goldschmidt really, really didn't understand, it wasn't until Beta, many years later actually, Hans Beta was one of the first people to really discover how these kinds of phenomena work. We're still working on it. But I want to point out that we have the most abundant transition metal on this planet and in many planets in our solar system is iron. But then we have the big six. So I want to explain the big six. There's hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus. Those six elements are comprising virtually everything in your body. The proteins, the nucleic acids, the carbohydrates, the lipids, fat. So we have to rearrange bond energies to get from carbon, which is normally associated with an oxygen molecule on this planet, or with a hydrogen molecule sometimes, to form methane, to rearrange those so we get carbon-carbon bonds. Carbon-carbon bonds are not easily formed. So I can make, for example, we can imagine very simple carbon rearrangements with oxygen. So carbon dioxide, for example, can be with light providing an energy source to make formic acid. That's one reduction, one covalent bond of hydrogen with the carbon. But to make acetate, a carbon-carbon bond, really, really, really hard. So this is what catalysts in biology do, is they make carbon-nitrogen bonds, carbon-carbon bonds, carbon-hydrogen bonds, and so on. So these are the big six. They can be rearranged many different ways to spell schnapps or however you want to do it. And then there are these 54 other trace elements. So if I take and grind you up and put you into Rob or your ears ICP-MS, we'll find a bunch of elements. For example, copper, manganese, magnesium, iron, calcium. So here's the story. And this is why I want to get to the life-to-life story. Life is electric. And here is where geologists generally don't appreciate this part of chemistry because it's biologically driven for the most part. We move electrons around. That's what we're doing. So you're sitting here in the room, breathing. You're putting hydrogen atoms, not just electrons or protons, but the whole atom of hydrogen onto oxygen in the air and breathing out water, as well as carbon dioxide. So that's an electron transfer reaction. And it's catalyzed by a group of proteins called the Oxido Reductases. This is a class of proteins. So biochemists have classified proteins into 6 buckets. The first bucket is called the Oxido Reductases. This is enzyme commission 1. So if you see an EC1, bop, 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 4 numbers after it, that's, so EC1.1.1.1, the first one, is alcohol dehydrogenase. So if you're drinking alcohol ever, you're moving electrons around, and you're dehydrogenating alcohol to make CO2. So in biology, just like in every other electronic system, substrates and products must be cycled. So you have half cells. You can't have a half cell without another half cell. So for example, all biological processes are paired, photosynthesis and respiration being the one that you're most familiar with. So in the Archean oceans, before we generated oxygen, there were lots and lots of sources of reductant. There was H2 gas itself. There was iron 2, as I described. There was H2S, hydrogen sulfide, and reduced organic matter, which was preformed from, for example, chondritic meteorites. Now, if we take a look at this, and this is really where I find the field of biology to be somewhat interesting, in that we can write these rather trivial equations, right? So this is water and carbon dioxide. We're going to take the hydrogen, put it onto carbon. We're going to make a reduced molecule here. This is basically sugar. This is a shorthand notation for sugar. So it was glucose N would be 6. And then we generate this extra gas, oxygen, and you and I are sitting in a room doing this. Now, when I was around 9 or 10 years old, I went to the Museum of Natural History to the planetarium. And in class, I guess it was in 5th grade, and it was explained to us by the lecturer that we're the only planet in our solar system that has oxygen on it. So I was rather taken with that. And I just assumed that some adult knew how this reaction worked. But they wouldn't tell me because it's too complicated. You know what? We still don't really know. We know the enzymes, we know them in detail. And I'm going to explain to you something really fascinating because I know we're in silos. But 2 buildings away from here, it used to be in this building, but 2 buildings away from here is the proteomics building. So Rutgers University used to be at Brookhaven, ironically. And I guess I follow the proteomes. But the protein data bank in the proteomics building is the reservoir of all of the structures of proteins that are published in the world. And we know the structure of the enzyme, which I'll show you in a bit, that splits water. We know it at incredible angstrom detail. We know it at 1.95 angstroms. This is, it doesn't get better than this. We know every single atom in that molecule. It's actually a very large molecule. Every single atom. We don't know how it works. And here, this reaction depends on manganese, 4 manganese atoms. This reaction, which you and I are doing, is dependent upon iron and one other very important transition element, which is copper. So everybody that is breathing oxygen uses copper. So this is the source today of liquid water. It's the major source of protons and electrons. So the oxidation of water requires, at pH 7, 0.82 volts. That's not a huge number. So if you think about it, this number is in the visible light range. It's actually occurring, it's a little bit overpotentialed, which means we take a little bit extra energy out of it, so it's not 100% efficient, but it occurs in the red light at 675 nanometers. It's actually 682 nanometers. Red, about the color of your shirt. So that's not high energy. So if I take a light and I just put light with red light on a glass of water, nothing happens. You don't get oxygen. So the catalyst here is the really important thing. It's moving the energy in a very concentrated way to break that set of bonds. And you never generate H or O. You always generate O2. And the H is actually protons. The electrons are going somewhere else. They meet up with the protons later in the game. So this is an actual photograph from Apollo 7 or 8. And this is the amount of water on the surface of our planet that we just took and put in a bowl. It's rather remarkable to me. If I go back 3.8 billion years to present day, we've always had liquid water on the surface of Earth. There's no other planet in our solar system like this. Mars had water, it's gone. Venus probably had water, it's gone. So we live in it's a Goldilocks world. And it ain't a whole lot of water, actually. There are probably about 2 or 3 or maybe 4, 5 oceans beneath the ocean. So maybe it's 5 marbles. Now, I'm just not going to go into the details here because it's going to be rather uninteresting, but I just want to show you the Rube Goldberg type of apparatus that actually splits the water. So these are the manganese clusters down here. It takes light energy and it oxidizes a manganese atom from manganese 2 to manganese 3, and ultimately a second photon comes in, oxidizes to manganese 4. And it does this for 2 manganese atoms. So it's 4 sequential, 1 photon hits that oxidizes water, and you get 1/2 of this O2 ultimately from one water molecule. The protons are dumped inside of a membrane here. So we acidify this. This becomes very acidic. It becomes about pH 4. This is pH 7.5. And this machine over here is an amazing machine. It's inside your mitochondria. The protons run through up this channel, and this machine actually spins. It actually physically turns, and it generates ATP. These are not figurative nanomachines. They're actual nanomachines. A second photon is arriving here and moves the electron up and moves it to this iron-containing molecule here, ferredoxin. It only carries the electron. And then the ferredoxin goes over to another carrier where it meets up with a proton again, and it produces a molecule which carries the hydrogen of that. So hydrogen is never allowed to be free in a cell. If the hydrogen is made free in a cell, it escapes. But by controlling it as an ion, a proton, and an electron separately, you can control the flow of the hydrogen to where you want it to go. Through carriers like NADPH, flavodoxin, and so on. So this machine contains 140 different proteins. That means 140 different genes. We're not exactly sure when physically this evolved. It's not constrained within plus or minus about 800 million years, believe it or not. This machine and this machine have virtually no sequence homology. That means if I put them and I map them together, I say how many amino acids in a row are in this one machine, and in the other machine, there's only 8% homology. But we think that they arose in a single organism at once and then diverged. So that's evolution. And this machine here is in your mitochondria. It's helping you make energy, helping you breathe the air. So one is making the oxygen. This is the only machine on the planet, the only one that generates oxygen. It's the same machine in an oak tree and in a cyanobacteria. In anything that's green or red that's photosynthetic, it's the same. All right. So here's an example of what that machine looks like. If you go to the Protein Data Bank here at Rutgers, PDB, you can pull up the structure of photosystem 2, and you can turn it on your computer. There's a little program that you can download for free. It's called PyMol. And here are the 4 manganese atoms. So here's the manganese. 1, 2, 3, 4. Cool. So there are several people in the world. Chuck Disputes in this building is trying to replicate that type of machine without the biology, to make a catalyst that will split water. Why would you do that? If you can make a catalyst that can split water with the energy of the sun, that's very efficient, you change the world. You just make hydrogen. You now have basically a non-polluting source of an energy carrier. So Dan Nocera at Harvard, who was a graduate of this chemistry department at Rutgers, he's at Harvard University. He has a catalyst that's made out of cobalt. Chuck has a catalyst that's made out of iron. Gary Brudvik at Yale has a catalyst that's made out of cobalt and iron. Nate Lewis at Caltech has a catalyst. And there are very many types of people that are working on this, because this is really, 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 really one of the most fundamental things you could do if you're interested in chemical chemistry. Now, obviously over geologic time, these very small nanomachines have been incorporated into many, 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 many organisms of different flavors. And so they're on land, they're in the ocean, and you can see they generate a carbon flux that is based on oxidation reduction reactions. This is not silicate rock weathering. Now you're reducing carbon, so the reductant now is the candy that you can store in the lithosphere, and the oxidant is oxygen, or the product is oxygen. So I always give this as a question in my course. If you were to take all the oxygen in the atmosphere and put it back into the ocean, how high would the sea level rise? The answer is about 1 meter. So Dan Nocera would say, if you give me a swimming pool worth of water, and I can oxidize it to make hydrogen, I can run New York City's electric demands for an entire week with one swimming pool worth of water. That's how much energy there is in the bottles. Amazing. The biological pump allows this material to go into the sediment, become stored in the lithosphere, and over geologic time, we go from a reduced to an oxidized world. And many metabolisms follow this world. So the earliest metabolisms are not oxygen dependent, obviously. So there's respiration absent oxygen, so you need another source or sink for the electrons. And then you can get to places where you have weak oxidants, and then finally strong oxidants like oxygen. We could go to a stronger oxidant on a planet, in theory. We could have a world of chlorine gas in the atmosphere. That's a very strong oxidant. Just saying. You would damage many, many, many molecules with such strong oxygen, and oxygen itself is a very, very dangerous molecule. So you can create reactive oxygen species like peroxides, superoxide, and so on, and your body's defenses are there to destroy those molecules because they will kill your DNA, they will oxidize your proteins, they do lots of damage. I always make a joke to my students, if you're running, you're really killing yourself. First of all, you only have 1.5 billion heartbeats on your life. So you can use them any way you want. But if you're going to run, you're just generating a huge amount of superoxide. And you're just going to make your life extend short. So don't run. Don't do exercise. It's not good for you. All right, so now we can take all those metabolisms and make a wiring diagram. And this is the wiring diagram of Earth. This is how all those electrons are connected in metabolism from different bugs. And then I asked one of my graduate students, so I usually put this slide up because it's actually easier to understand the London Underground than it is to understand the diagram that Potential and I did along with. But it's basically this kind of electrical circuit in which electrons are getting on and off the bus instead of people. And you say, okay, how many genes did it take to invent this entire global pattern? There are only 400. Only 400 proteins on the planet can make that entire electrical circuit work. So now you have one power supply, the sun. You have two wires, the atmosphere and the ocean. Right? The atmosphere and the ocean are wires. And everything else on the planet that moves the electron around is basically a transistor. And we can put all those metabolisms together like this. This is not so interesting except for those of you that are interested next week. Rohir Brockman is coming from MIT, and he's going to talk about this reversed tricarboxylic acid cycle and other cycles here. This is the evolution of metabolism in a very simple Venn diagram. So I think about it like this. So I did take electrical engineering, and I do think about the surface of the planet being one big circuit board. So I told you, there's one power supply, two wires, and then we have these transistors, and this is an example of what one of the cores of the transistors looks like. So that's the doping agent of one of the transistors in a protein. It's a 4-iron, 4-sulfur cluster. That's a natural mineral. So if we take a look at all of the proteins, those 400, that run that circuit diagram, and I ask what are the distribution of the doping agents, these are the distributions. We have approximately 2/3 of them are based on iron, either as a heme. This is coordinated with an iron, a nitrogen-containing 5-membered ring. That's what makes your blood red. Or that iron-sulfur cluster type material that I just showed you, with copper being the next most abundant, manganese the next, nickel the next, molybdenum the next. Very, very small numbers of other transition metals. This is the close-up of that 4 iron 4 sulfur cluster from the protein data bank. So here you can see it bound. It's bound to 4 molecules that contain sulfur group in the amino acids. So this is cysteine. So this is the 4 iron 4 sulfur cluster. This is the second most abundant motif of the transistors in life. It's one of the earliest. And we just published that paper 3 weeks ago. If I go to nitrogenase, this is the enzyme that fixes nitrogen, takes it from the air. Nitrogen is an inert gas. It's almost like a noble gas. You have to grab this gas and put electrons and protons on it to make ammonia, otherwise you don't have any life. Basically, this is bunches of that same iron sulfur cluster motif, except now instead of having 2 iron or 4 iron 4 sulfur, you have 38 irons and 38 sulfurs and 1 little molybdenum molecule right there. Atom, actually. And then you have something like this, which is superoxide dismutase. This is one of the enzymes that's protecting you from killing yourself when you run. And it contains 2 copper atoms. Now, let me just go back for 1 second.
Are those the selenium there also?
There is selenium we can oxidize too. So, Nathan E. works on selenium and arsenate oxidation. These are very interesting reactions. If I take a 4 iron 4 sulfur cluster, it's very easy to find this mineral as a mineral in nature. So we can appropriate already a natural mineral into a protein to make a catalyst. So it's easy to see how that happened. It is very, very hard to see how that happened. It's easy to see how this happened, but I'm going to remember now that 4 manganese cluster that was in the water splitting complex? There are 31 minerals in nature that have 4 manganese atoms in a cubane structure. 31. None of them that we know of can split water. Nature appears to have made and incorporated manganese into a mineral that doesn't exist in nature. So we took already something like pyrite and made electron carrier out of it, but where that 4 manganese atom came from, structure, nobody knows. And then of course there's manganese itself, which can often react with oxygen, so we make another superoxide dismutase with just manganese itself. All right, so when I take and look at all those motifs, there are only 35 in nature. This is like taking minerals and saying how many different mineral types are there? Mineral types, not minerals, mineral types. There are very few mineral types. You can have silicates, you can have oxides, you can have sulfides. There are only 35 motifs. I'm talking about structural motifs. So I challenged one of my students to develop an evolutionary history of these motifs, and here they are. So there's the 4 iron 4 sulfur cluster, and it makes already the ferredoxin, that's the guy that collects the electrons at the end of photosystem 1 that I showed you a long time ago. It also can make hydrogen gas from protons. This is a very, 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 very early metabolism using hydrogen. And here you see one of the last enzymes that evolved is in you and me in our cytochrome C oxidase in our mitochondria to breathe oxygen. Now, I'm just going to finish this talk up. So, the top of the atmosphere, we have solar radiation. And I know some of you in the room remember this, some of you don't. So, if I look at these lines out of our sun, why are there lines absorption lights in our cell. Student? Any student know? The Fraunhofer lights? This isn't noise. When you see a spectrum like this, you're looking at the spectrum of elements that are in the corona of our star. For example, iron. They were discovered by the German spectroscopists, most notably Fraunhofer, Lyman also. By the way, and I'll just make this, I said this to Claude's class, I think. Remember the hydrogen helium, very beginning? Helium was discovered by the spectrum of our star before it was discovered as an element on the planet. It's called helium because it comes from the sun, helios. It was predicted before it was actually physically isolated. So you take this spectrum, and in the present world, at the top of the atmosphere we have this, but we trim off virtually all this UV light today because of ozone. And now we're looking at absorption bands of molecules, not elements, mostly. And then, of course, 10 meters below the surface. Now, here's something that I think most oceanographers don't appreciate until they take some optics. Seawater without organic matter, this is called case 1 water, that's the oligotrophic open ocean, is relatively transparent to ultraviolet radiation. So if I have ultraviolet radiation, it'll actually go into the ocean quite deep. And this is what my student John Kim did a few years ago. He took siderite, which we made in Nathan's lab. So that's iron carbonate. We irradiated with ultraviolet light. It has an antibonding orbital, which I'll show you. Those of you who don't remember antibonding orbitals, it just, I won't go into it now. It's just a sum or a negative part of molecular orbital theory. We can populate that antibonding orbital at about 275, 280 nanometers. And you can see here, with just light, we've made rust. There's no oxygen here. This is a quartz cuvette. So that goes back to how we can oxidize iron in an anaerobic world sacrificially and generate oxidized iron in York heat. It's actually a very complicated reaction, and it's a 2-photon reaction. And what is the product? Follow the electron. Where did it go? It produced hydrogen gas. So very, very, very simply, by taking siderite, putting it in UV light, you can generate a hydrogen flux that's quite large. It's aqueous. Now, let's go back for a second. If you have an aqueous surface, and you have a UV flux, and you can oxidize the iron, what happens to the carbonate? It becomes a gas. So when we published this paper, I sent a preprint of it to Grotzinger, John Grotzinger, who was head of the Mars Curiosity mission. And I said, John, that's why you have red regolith on Mars, and the carbonates are gone. You had a surface of Mars that was damp or wet with a high UV flux of siderite. It's photo-oxidized. It becomes red. The carbonate goes back off and ultimately was blown off later on when Mars lost its magnetic shield. Winnie, present graduate student, is continuing this work with manganese. And so she's been working with manganese carbonate and other manganese molecules and you can photo-oxidize manganese with UV light. Now this is where we're a little bit murky. We know we can generate formic acid from this reaction. No biology. So we're generating an organic molecule. The organic molecule also can be destroyed by the UV light. So how you would preserve this in an Archean ocean, I'm not sure yet. But I just want to get back to this because I think it's really, really, really exciting. So years ago, we had the Terrestrial Planet Finder mission, which was scrapped from the Decadal Review. There were two parts of this mission. One was called a chronograph, and the other was an interferometer. The interferometer was to fly at the L2 point, which is, the Lagrangian 2 point is about 22,000 miles out into space. It's a point of equal gravity between the Earth and the Moon. So of the various Lagrangian points, this one is a very preferred point for stability for telescopes, for example. It's where the James Webb Telescope ultimately, if it works, will be. NASA scrapped this because it was deemed too risky to fly multiple satellites in formation that had to be within a few millimeters of themselves all the time. But the chronograph lives. So the Decadal Review, which is what I'm working on now, will try to resurrect the chronograph. So the chronograph can also act as an interferometer. And why is that? Why do you want that? You want that so as a planet transits its star, say 6 or 8 or 10 or 12 parsecs from here, we can black out the visible light of the star and look at the infrared light of the planet. And why do we care about that? Hold on. Sorry. Because there's a heck of a lot of information in the infrared about gas composition. So I can see methane, water, nitrous oxide out here. Now the stare time required to generate enough photons to make a spectra of which you have reasonable confidence is about 1 month. And now it depends very, very much on the size of the telescope. So what are people trying to do to get around this? They're trying to build 90, 100-meter telescopes on land. You can't do this in space. And how do we get around this atmospheric problem? We're looking through our atmosphere at a star 5, 8, 10 parsecs away. They use the Doppler shift between us and the target to cancel out the background noise of our atmosphere to generate the spectrum of the target of interest. And there's a second phenomenon which I find absolutely amazing to me. And that is if there is another star in the nearby orbit of the first target and it comes in front of you, you can use the gravity of that star to lens the photons to your telescope. It's called gravitational lens. You can increase by a factor of an order of magnitude the number of photons. So instead of staring at something now for a month, you could stare at something for a few days or even less than a day, depending on how far away the target is. So if you are thinking about things like astrobiology, it's a very, very exciting time. So this is, I think, the lowest from other planets is going to be something that we'll be looking at now in planetary sciences for the next 30, 40, 50 years, even more. So to give you an idea, the planetary scientists are planning missions 30 years from now. That's the target that they think about, 30 years. Because already 5 years or 8 years is done, it's cooked. Baked in the cake. All right, so I wanted to give you some feeling for how transition metals on this planet became incorporated into molecules that evolved to move electrons around that create life. And there are very few transition metals you have to worry about. Iron, copper, a little bit of manganese, a little bit of magnesium to some extent, although magnesium is not a transition metal. A little bit of molybdenum. Don't worry about zinc. It doesn't behave like a transition metal in our bodies, although it's found. And to wrap this up, the way I think about it is the first half of Earth's history was what I call a research and development phase. This is when the Microsoft microbes became kind of active and started to think about different pathways, some of which made it to the end and some of it just died. So we're only left with about 400 genes, of which there are only 35 motifs. So Microsoft really wasn't that creative in the microbial field. And then all of these key metabolic processes developed in single-cell organisms. All of them. You and I and every other eukaryote that you ever met, as one eukaryote talking to another, we're not really interested. And the entire potential of electron motion on the planet would, and I will even argue with the hydrothermal vent people on this, is driven by life. And why would I argue with the hydrothermal vent people? Because the redox gradient of a hydrothermal vent is between the oxidized outside water and the reducing fluids that are coming through the vent. So the oxygen in the outside water is producing a huge redox gradient that's based upon life 2,500 meters above, that's generating the oxygen from life, and is mixed down into the ocean interior because of ocean circulation. All right, thank you.
Paul, can you give us the latest on photodissociation of water to make oxygen with hydrogen escape? What's the thinking, especially in a Precambrian where you may have had a warmer climate, you could have thunderheads penetrating into the stratosphere that would sort of aid that process? What's the latest on that?
The latest is a little murky. So the old papers were by Berkner and Marshall in the late 1960s, early 1970s, that claimed that you could have a photolysis of water that generated oxygen. Jim Casting himself then poo-pooed that. Now, we know that there's oxygen, there's a little bit of oxygen on Mars. Surprisingly to me, there's an awful lot of oxygen apparently in the ice on Europa. That's not from radiolysis, it's from radiolysis, it's not directly from photolysis. So those are coming from high energy electrons. But yes, in principle, you could do it. Now, why doesn't it, what's the problem? So let's imagine that it takes light energy, let's say 215, 240 nanometers, pretty heavy UV to oxidize water. That will happen, but you'll build up ozone, and it becomes self-quenching. So that was the original pushback when we started to figure out that ozone really was a feedback mechanism that didn't lead to a large contribution of oxygen on the surface of the planet. But if you go back to any of the books, even Dick Holland, you will never find zero oxygen on Earth, in the early Earth. You'll never see it as zero. It's always a small number, like 0.01%, 0.001%. We don't know. But there's always given a little bit of oxygen fugacity in the early Earth. And that has to have been abiotic.
What's Casting's mechanism for the abiotic oxygen?
High energy, photons or electrons, or any particle. So it's just energy.
And so it doesn't run into that self-quenching?
It does, it will run into the self-quenching. So yeah, going back and forth with Dickie Meadows, Dave Crisp, you know, people Roger Summons. Roger Summons would say oxygen could be a false positive. If we find oxygen false positive, you know, I would say this: if I see oxygen and say methane on a planet, you've got to say life. There's no rational explanation for the very extreme ends of an oxidant and a reductant to be together without.
If iron can be oxidized via light, does that affect at all the idea of using the red beds as a marker for biological oxygen?
In and of itself, red beds is not a marker for biological oxygen. So I think if you go back before you were born, we started to ask, when did we have oxygen on the Earth? The nominal explanations would have been based on the oxidation state of uranium. So we would have had uranium-40, uranium-6, okay, as a marker for oxygen. So that was one marker. The red beds themselves were often used as a marker as well. I think we became much more convinced of the oxidation state of the planet with the development of the mass-independent isotopic fractionations of silver. And, you know, it's one of those things. James Farquhar is really smart, but had he not been a postdoc in Thiemann's lab, I don't think he would have come up with this explanation. So, Mark Thiemann's is at UCSD. He's in physically the same lab that Harold Urey used to be. Physically. But he was a student of Clayton, who just died a few months ago at the University of Chicago. And those guys really, really were extremely good at figuring out the basic idea of photochemistry of an isotopic fractionation. And you know, at some point, if I don't think Mark has ever been to Rutgers, but we should definitely invite him to give a seminar here, because he's one of the great thinkers, especially where we got water from, why nitrogen isotopes are so widely variable across the solar system in terms of the isotopic fractionation. It's really very...
His question, now in the ocean, the primary species of iron-3 and orthogenic minerals in the bottom in the sediments is called iron oxyhydroxide, some big species of OH and oxygen. But the first product to form, if you put iron-2 into the ocean now, is FeOH3, and then it ripens to other minerals in the presence of oxygen. So if you had the Greenland iron-3 formations forming without oxygen, would you be able to see that in the mineralogy of the formation? Because
yes,
you would presumably never, FeOH3 would still be the immediate product.
That's true. It is.
And you would never get to
the more oxidized
species. So don't we know that? Can we look?
I don't know. Do we know exactly the fugacity at which these reactions occurs over time? Do we know the kinetics of it?
Well, we know the kinetics. Yeah, we can do the kinetics, and we could calculate what the kinetics would be at very low oxygen tension, if that's what you mean.
The biggest disappointment for me in discriminating most of these reactions, whether it was dependent on oxygen, not dependent on oxygen, was we can't use it appears we can't use the iron isotope fractionations to discriminate one reaction system over another. They're all kind of overlapping. So I was really hopeful when we had the ability to have multi-collectors ICP-MS that we would, you know, solve this problem. It doesn't work that way. But to talk to you about the mineralogy, that would be fun. Yeah.
Going back a little bit here. What you're saying implies that there is a generation of stars in which it is impossible to have had life. That is, the ones that bear supernova product elements.
If they don't bear supernova product elements, yes, that's correct. There's a certain generation of those stars that will not have
first generation.
Right.
So that's fair enough. Switching subjects slightly. Doesn't your system quench itself as soon as it starts producing oxygen?
No, because it's not using UV light. Oh, my system?
Yeah, the UV-driven
yeah,
system.
it's not generating oxygen. It's just generating hydrogen, okay, and carbon dioxide gas. It's nothing.
It's oxidizing the iron and the other things.
Exactly.
Okay.
So it's just reacting with water. This is why the moon is not red. mean, the moon also has siderite, but it's not red. It has iron, but it doesn't go anywhere. There's no, it just doesn't go anywhere because there's no aqueous. Yeah.
Did you get a response from the JPL team when you talked about the siderite?
Oh, no, yeah, of course. Rotz was amused. I wanted him to do a simple experiment. So they can take and scrape away the regolith at the surface, and it's gray underneath, right? So there's a lot of stuff on Mars that I think is very cool. So I said, why don't you squirt a little water on there and see if it becomes oxidant? Well, they don't have squirt bottles on rovers, so apparently this is another mission. Probably they tried something like this on Viking, but they didn't have the ability to look at the oxidation reduction kinetics of that. So Viking was amazing. For those of you that think about back in time, 1972, right? So we don't have these things. Computers are as big as a room. Jerry Soffin, who was the team leader of Viking, he had a $2 billion budget in 1972 for the Viking mission. So he built everything in duplicate. So he had 2 landers and 2 orbiters. And he went to JPL and he said, I need to get a mass spectrometer on my landers. And they said, there's no way we can put a mass spectrometer on that payload because it's going to weigh too much. He said, I got $2 billion. I'm going to go to Goddard Space Flight Center. They'll do it. Oh no, we can do it. We can do it. So he actually had competitions between different NASA groups to make these instruments as small as possible. And now, of course, putting a payload with a mass spectrometer, a GC mass spectrometer, in fact, on Europa is not a big deal. So there's a 45 kilogram payload for science on the Europa mission, the Europa Clipper. That sounds like a very small number, but that's a huge number, actually. The mass spectrometer, the GC mass spec, weighs something on the order of about 15 kilograms. It's really amazing. Yeah.
One more question. So in the Archean, you had photosynthesis. You had cyanobacteria, presumably, whatever you want. I mean, that's what. And so organic matter was being created. What happens?
It stays in the lithosphere, but so let's think about that for a minute. There's nothing eating you.
Now, but then the carbon isotopes are kind of more or less leveled. You go through as far as you compile these, so it suggests that the burial rate of the organic to inorganic is about the same as today. So that's, how do you do that?
No, it's not. Well, so yeah, this is a very interesting problem.
If you don't have oxygen to sort of take some of that organic matter back into the system.
So there's photosynthesis, but you're not generating oxygen.
Right.
Okay. So you can generate organic matter. Okay. You don't have a bug to eat you. So the flux of organic matter, presumably into the sediments, is lower. So the flux of organic matter today is driven by zooplankton that produce fecal pellets that sink rapidly, or by large cells. So I think it was when Claude was giving the talk. I think it was. If we go back just a few months ago, Joachim Brox has the second pulse of oxygen. We know pretty sure that this is real. This second pulse of oxygen in the neoproterozoic. Okay, so you have this first pulse of oxygen here. We don't know that number. That's maybe 1% oxygen, 2%. Nobody really knows the number. But then you have this second pulse of oxygen in the neoproterozoic. I think you were the one that was invoking the sturgeon as a mechanism for driving this, right? So it was silicate weathering as well, right? And then it was the production of phosphate into the ocean, right? Through the last glacier, last snowball.
Falkowski and Brox.
Right. But Brox now has a very interesting idea, which is from the fossil record. And this is really a place where the fossil record is helpful, is that you get rise to these large eukaryotic algae. Like, we don't have diatoms yet, but there are large eukaryotic algae that are in a great abundance here.
Yeah,
And
but after that, there's all kinds of stuff. But what about all the 2 billion years before? What are you doing with all that organic material? I mean, what's limiting the oceans from producing a gazillion cells? You have phosphorus, you have all the main ingredients. Why not productivity?
You do and you don't.
Why not productivity the same as today?
Well, okay, so you have riverine flows of phosphate. You have to fix nitrogen. And so here's where things get really, really, really murky. So nitrogen fixation is all prokaryotic in the ocean. It's limited by iron. It's limited by iron. So the major source of iron here is going to be dissolved iron. This is not going to be a limitation. So here's what happened when Linda and I were starting to think about this a long time ago with Joe. Why do you even get this first burst of oxygen? So let's just think about this for a second. So here's where feedbacks come in. So this is the nitrogen cycle. N2 gas goes to NH3, 4 plus, doesn't matter. In the absence of oxygen, that's the end. That's it. That's it. Nothing else happens. In the presence of oxygen, and only in the presence of oxygen, does a bug take the ammonium and goes through NO2 minus nitrite to NO3 minus nitrate, and under a very small amount of, we get into anaerobic conditions or low oxygen concentrations, this becomes an electron sink. So this is converted then to NOx, which is a gas. For example, nitric oxide, NO, or nitrous oxide, NO2, laughing gas. And then this goes back to this. So this is an entire cycle is driven by biology. The entire nitrogen cycle is driven by biology. So here's the problem. And this is, if you don't have oxygen, you're stuck here. If I sink this into the sediments, I'm sinking ammonia. Very, very, very precious. So that world has to be, ultimately, a nitrogen-limited world. It has to be. So,
but if it's unlimited in iron, you can still fix a lot of nitrogen.
yeah, but you ultimately, I mean, this is a very expensive process, right? That's
If you have iron and water.
It's very expensive. So this is, huh?
Expensive, but you have the energy from the sun. So.
Well, you do and you don't. I mean, the point of every microbe is to grow. And if every microbe can cheat and get your ammonium and doesn't have to fix its own ammonium, then it wins, right?
Yeah.
So this is one of the big, big, big problems. This is what's called the black queen problem in microbiology. So you cheat. You get somebody else's nitrogen for free. And those poor suckers, I mean, let's go, just think about this for a minute. Why do we get into this argument of why there's phosphorus versus nitrogen limitation in the modern ocean? Because the geologists, like Wally, read papers by Redfield. And Redfield went to, when he looked at the Redfield ratio, so the Redfield ratio, canonical Redfield ratio, is 106 carbon to 16N to 1 peak. Right? That's the Redfield ratio. If I go out into the open ocean and I look at the N to P ratio as a function of depth in the ocean, okay? So the N to P ratio will flatten out to some value in the Atlantic or the Pacific or the Indian Ocean. It's not 16 to 1 ever, except in the Mediterranean basin. This value is, in the Atlantic Ocean, it's 14.78, 14.8, for example. In the Indian Ocean, it's 13.5. It's missing N. Why is it missing N? Because when you have less oxygen in the ocean interior, the nitrate becomes denitrified to this reaction and it blows up into the atmosphere. And this is why the nitrogen isotopes in the deep ocean for nitrate are +6, +8, +5 canonically. Because the light isotope is going up. So the idea here, so when Redfield did this, he realized, he knew that he was missing a nitrogen. He knew it. He knew it. In 1958, he had a really good paper in the American Journal of Science. And he went to Hutchinson at Yale. And he said, why am I missing nitrogen? And Hutchinson said, you can't be missing nitrogen because it can always be fixed from the atmosphere because you have, and he didn't know about iron limitation. In lakes, that's absolutely true. So virtually every single lake in North America is phosphorus limited. And Hutchinson embedded that idea into Redfield, that it should be a big lake. So Redfield writes the paper, Broker reads the paper, Broker says phosphorus is limiting, and that's the end of the game. So every student of Broker, every one of them, Jorge, Mike Bender, all of them, Steve Emerson, they all, phosphorus canonically is limiting.
Tyrell.
Yeah, Terrell too. But then you have people like Epley, Dugdale, and so on in the 1960s going around saying, why don't we see phosphorus limitation? And then they start realizing that nitrogen fixation in the open ocean is really, really, really hard to find. There are very, very few nitrogen fixers. So nitrogen actually is limiting in the ocean today. And I would argue that it's been limiting forever, basically.
In the interest of time, I think you'll comes around.